Okay, welcome back. Before we go over the questions on the next page, there were two videos I wanted to take a look at to review nuclear power. The first one is this one from Bill Nye, and he goes over half-life. Okay, we're going to take a look at some of the advantages of nuclear energy and take a look at the amount of waste that's produced.
Now, the persistent paradox that is nuclear power. It's efficient. One train car full of nuclear fuel can keep a nuclear power plant running for a year. But it takes a whole train load of coal every day to keep a conventional power plant running.
So in that little clip, you saw how much coal it would take. It takes a train load of coal every day to run a regular coal-fired plant. And remember, the coal, mining it out of the ground, creates a lot of environmental problems, hazards for the miners. Coal itself has uranium in it, so it's radioactive, produces acid rain. Nuclear power plant only uses a small amount of fuel.
There are a lot of things to be afraid of when it comes to nuclear power. There are meltdowns where the uranium metal fuel gets so hot that it burns a hole through the reactor and the whole thing explodes. There are terrorists who could get hold of some of this nuclear material and make the events of September 11th look like getting a parking ticket. The real terror, the real danger, the real horror of nuclear power may come long after the power is generated with nuclear waste. Now, do science and society have an answer for this problem? Well, let's have a look. A nuclear power plant can generate a lot of electricity, but in nature, we don't get something for nothing. So when we generate electricity, we also get tons of radioactive waste. How much waste do you make in 60 years?
Well, in 60 years, we would produce enough waste to basically fit contained into a convenience store.
That's not very much.
Well, it's not very much when you compare it to like a coal plant where, you know, its waste of all the coal that it uses and emissions into the environment.
It's probably 10 million times that.
Yeah.
So the stuff is dangerous.
It's dangerous, but it's contained in a small volume.
The fuel rods are taken from there into this pool. This is where they're stored for years. When they first come out, they're too hot to handle. They cool off, and then they're eventually taken to dry storage. There are reactor pools like this all over the world, just waiting for a place to put the waste.
Now listen carefully as this man explains how long the containers are good for.
What is this, Larry?
This is a dry cask storage for spent nuclear fuel.
Is this radioactive?
There's radioactivity inside it. We've got concrete overpack that protects us from the radiation.
How thick is that?
Oh, it's about 22 inches. Total about 24 inches, including the steel.
You can just stand right next to these. You can touch these.
Oh, yeah. It's completely safe. And you can see by looking at the meter, it's less than 1 millirem per hour on contact.
Barely a millirem. Put that in perspective. What's a dental X-ray?
Dental X-ray is probably about 20 millirems.
So right up next to it, it's less than an X-ray, which is only on for a few moments.
Yes.
Right. Suppose we just left it here. How many years or centuries would it take for this stuff to become benign?
The current average estimate is about 10,000 years.
Now notice how he said the stuff would be harmless in 10,000 years. He doesn't want to contradict the power plant, but really most people consider it to be a much longer time. We're going to take a look at that in the next clip when we look at half-lives.
10,000 years. That's a long time.
Yes, it is.
There's something about these that doesn't look like they're good for 5,000 years.
No, they're not.
Yeah.
And then they both agreed that the containers probably are not even going to last for 5,000 years. Now in this little segment, Bill's going to explain half-life. Basically, a half-life is when the stuff comes out of the nuclear reactor. We think of this being all radioactive. And then in one half-life, half of that becomes harmless, it breaks down. And then the half that's left takes that long again. So he's going to use colored water to demonstrate what its half-life.
We measure radioactivity in what's called half-lives. You see, the atoms in radioactive material spontaneously just break apart or decay. Now, we can't tell when an individual atom will decay, but we can tell when a fraction of them will. So a half-life is the amount of time it takes for half the atoms in a piece of radioactive material to break apart. Now,
so that's any sample of radioactive material. So half-life is how long it would take for half of those atoms to break down and become harmless, so that it wouldn't be harmful to human beings.
plutonium has a half-life of 24,000 years.
Now notice that the half-life of plutonium, which would be in the radioactive waste from the power plant, one half-life is 24,000 years. And the man told us the container wasn't even going to last for 5,000 years.
So let's say this red water is the plutonium in a spent nuclear fuel rod fresh from the reactor. Well, after one half-life, 24,000 years, diluting this water by half, it looks like this.
So this would be like the example that half of the atoms, or like half the colored water, is not harmless. So he diluted it by half.
After two half-lives, 48,000 years.
So then he took this and diluted it by half again. That's to simulate half of the atoms becoming harmless again. So it's like diluting colored water by half.
Years, it would look like this. After 10 half-lives, 240,000 years, the water starts to look pretty clear. Now, plutonium is notorious. It's especially radioactive. It's 20 million times more radioactive than uranium dug from a mine. You see, we're not talking about potato salad left out in the sun. We're talking about plutonium. Now, the legal requirement for storing this material is only 10,000 years. That would
10,000 years is what the man at the power plant said that he estimated how long it would take for the material to become harmless. But that's not even one, it's half of the one half-life. And you can see that the water still has a lot of color, so it will be very radioactive at the end of half of a half-life.
be over here someplace. That's not even half of a half-life.
And the second one I want you to take a look at is how the nuclear containers are made to store the nuclear waste, just to give you some idea of what it takes to store this stuff.
Designed to take the heat, the kind caused by the most radioactive of wastes, used nuclear fuel. These fuel rods are too dangerous to be casually disposed of, but encased in special spent fuel canisters, the risks should be contained. Nuclear waste sits in a holding pattern, and that means storing it in massive cylinders until there's a way to dispose of it. These containers start with a big rectangular sheet of stainless steel. A special circular cutter carves a beveled edge onto it. They feed it to rollers, which curl the sheet into a cylinder. It takes 4 trips through the rollers to really round it out. They tuck a template inside the curve to check the radius. Next, a welder joins the neatly beveled edges to complete the cylinder. This cylinder will be the outer wall of a canister. The canister will fit inside a bigger cylinder called an overpack. Its outer shell is 2.5 centimeters thick, about the diameter of an American quarter. Building a container to hold used nuclear fuel is a many-layered process. The next step involves the lid, made of multiple steel discs, with concrete placed between the steel layers like a sandwich. Incredibly, high-pressure water jets easily cut through the thick steel to produce the discs. A computerized tool cuts a grooved profile along the edge of each disc. They also machine the top of each disc to the correct profile and then measure to confirm it's exactly right. Next, a computerized laser slices through more stainless steel plating to produce long, narrow panels. Each is designed to fit together to create a grid of storage cells inside the canister. They line each panel with an aluminum alloy that's neutron absorbent, and they place a piece of steel sheathing on top of that. They weld the steel sheathing to the steel panel, encasing the neutron absorbent material. Working within a metal framework for guidance, they weld 4 of the lined steel panels together to create a fuel cell grid for one used nuclear fuel bundle. They then build a 68-cell grid. With that complete, they're ready to piece together all the parts of the spent fuel canister. They first lower the inner shell onto the base plate. The shell is held steady by a supportive structure as they weld it together at the seams. Moving inside, they install numerous bars to support the fuel cell grid. With the canister now wrapped in plastic to keep it clean, an automated cutter gradually shaves down the rim to trim it to the correct height. Precision is everything. Using a level and a laser, they ensure that the trim job is even and exact. Once they're satisfied, a crane carries the fuel cell assembly over to the canister and then suspends it above the open cavity. It dangles briefly as workers inspect the assembly. They give it the thumbs up, and the crane then lowers the fuel cell assembly into the cylinder. It's a snug fit, with just over a centimeter of clearance between the inner assembly and the wall of the cylinder. This technician inserts a camera into each cell of the grid and scrutinizes the image. He's looking for any debris that could hamper the installation of the nuclear fuel bundles. Both the cylinder and the fuel cells have been meticulously cleaned, but the camera inspection confirms they haven't missed anything. It's time to put a lid on this nuclear waste canister. It's a trial fit. The lid will be permanently welded to the canister later, once the used fuel rods are safely inside. The canister will then be placed inside the overpack, with concrete poured between the walls. That should keep the hazards of nuclear waste entombed indefinitely.
When we left off last time, I had asked you to start by answering these questions. So the first question, what percent of electricity is generated from nuclear energy? About 20%. Explain how electrical energy is produced using fossil fuels. Well, we have that process that we went through here. Okay, you burn the fuel to make thermal energy. The thermal energy you use to make steam. The steam spins the turbine. The turbine turns the generator makes electricity. How is electricity production different in a nuclear power plant from a fossil fuel plant? The first step is different. Nuclear fission splits the atom to make thermal energy. That's it. It's the only thing that's different. So how are they similar? Okay, after step one, they're identical. After you get the thermal energy is used to make the steam, to spin the turbine, to turn the generator, to make the electricity. What energy conversions occur in a fossil fuel plant? Well, we have chemical energy in the fuel to make thermal energy. Then we have the thermal energy stored in the steam. The steam is used to make mechanical energy when the turbine spins. The turbine is used to make electrical energy when the generator spins. So thermal to steam, steam to mechanical to electrical. There are some energy production methods that do not involve heat or steam. Okay, except for geothermal, the renewables do not use heat to make steam. So solar, hydroelectric, tidal, and wind. And then this last question says, draw a picture of a fossil fuel plant producing electricity. Make sure to include the energy conversions that take place. So here we go. We have thermal energy used to make steam, used to turn the turbine, used to spin the generator, and the generator makes electricity and sends it to the customers. Okay, we're going to stop there, and when we come back next time, we'll be starting a new unit on thermal energy. I hope you're having a great day, and talk to you soon.